All right, let's kick things off by looking at a pretty stark contrast. When we think of a standard chatbot, it basically just answers a question, right? You ask, what is BGP, and it spits out a definition. Boom, done. It's a very simple, passive one-to-one exchange. But an AI agent, that operates on a totally different level. Instead of just answering a question, it takes a goal. You give it a broad objective, something like, hey, figure out why the network is down. And it actually formulates a plan and takes action in the real world. It plans, acts, observes the results, reasons about what to do next, and honestly just keeps working until it gets you a result. It's literally the difference between asking a dictionary to define a word and asking a senior engineer to go fix a problem.
So welcome to The Explainer. Today we're cutting right through all the buzzwords to demystify AI agents and understand exactly how they work under the hood. Look, we hear the term AI agent tossed around a lot lately, and sometimes it can feel a bit like science fiction. But today, we're looking at the actual, concrete anatomy of autonomous execution. We're going to see how large language models are finally stepping out of their little chat windows to execute complex workflows in real enterprise environments.
Here is our roadmap for the day. First, beyond just answering questions. 2, giving the AI hands. 3, the agent action loop. 4, a real-world network example. 5, adding memory with RAG. And 6, guardrails and the complete architecture.
Okay, Section 1. Beyond just answering questions.
We really have to start by understanding the fundamental limitation of standard LLMs. They are incredibly smart, sure, but they're basically isolated brains. They have absolutely no network access, no SNMP, no SSH capabilities. If you ask a standard LLM to check a router's CPU, it's just going to tell you, sorry, I don't know, because it simply cannot touch the outside world. It can only generate text based on the static data it was originally trained on. Imagine having an absolute genius networking expert locked in a windowless room with no laptop and no phone. That is a standard LLM.
Moving right along to Section 2, giving the AI hands.
Yeah, this is where it gets really interesting. How do we let that genius out of the room? Well, the answer is something called tool calling. Instead of just replying to you with text, the LLM is trained to output a specifically formatted command, a tool call. So, it might output a request like, I need to run the getRouter_CPU tool for router 1. Then, the underlying system actually executes that script, reaches out to the router, grabs the result, let's say it's 92% CPU utilization, and feeds that tool result right back to the LLM. The AI didn't magically transform into a router, but we did give it the ability to ask our system to push the buttons for it.
And these tools, they can literally be anything. In a networking context, you might have common agent tools like get_CPU, get_memory, get_interface traffic, or get_syslog. The really cool part here is that the LLM doesn't need to know how these tools are coded under the hood. It doesn't need to write Python or know the API endpoints. It just needs the instruction manual. We tell it what the tool does, and the LLM decides exactly when it's time to reach for it to solve the problem at hand.
Section 3. The agent action loop. Giving an AI hands is fantastic, but it needs a cognitive framework to actually use them effectively. That brings us to the agent action loop. Plan, act, observe, revise, and act again. This right here is the heartbeat of autonomous execution. Confronted with a complex problem, the LLM doesn't just wildly guess the final answer. It stops. It creates a plan. Then it acts by calling a tool. It observes what comes back. And if that output gives it a new clue, it revises its plan, reasons about it, and takes the next action. This iterative loop just keeps spinning until the task is completely finished.
Let's look at Section 4, a real-world network example.
Let's see this build out in a concrete scenario, like diagnosing a network outage. Say a user says, investigate high CPU on router A. Step 1. The agent calls the CPU tool and observes it's pinned at 96%. It thinks, okay, high CPU, I need to find the specific process. Step 2. It calls a process tool, sees the routing daemon, RPD, is eating up 81%. Now it revises its plan. RPD is high, probably a routing protocol issue. Step 3, it checks BGP and spots a neighbor constantly flapping. Step 4, it digs into the syslog to confirm the BGP session is repeatedly resetting. Finally, Step 5, it synthesizes all those observations to generate a highly accurate root cause analysis. Just by following these steps sequentially, the agent went from noticing a high CPU to perfectly diagnosing a flapping BGP neighbor, with absolutely zero human intervention. It connected all the dots totally on its own.
Moving on to Section 5, adding memory with RAG.
Now, to troubleshoot like a true veteran engineer, our agent needs to remember past incidents. Think of it like this. Tools are the agent's hands, letting it execute APIs and query live data in the present. But RAG, Retrieval Augmented Generation, that is the agent's memory. It holds historical incidents, documents, and runbooks. Before diagnosing that BGP flap we just talked about, the agent can use RAG to search the internal knowledge base, essentially asking, hey, have we seen this exact issue on this router model before? It pulls in that historical context to make way smarter decisions right now.
Section 6. Guardrails and the complete architecture.
Okay, so now we have a powerful brain, hands, and memory. But that introduces a serious new challenge. Can the agent just freely change system configurations? Like, if it decides the best fix for a flapping BGP session is to completely shut down the router interface, should it just be allowed to go ahead and do that?
Absolutely not. Look, because agents can change the real world, they can also potentially cause massive network outages. So we absolutely have to implement essential guardrails. A chatbot giving bad advice is just a funny screenshot. An agent executing a bad command, that's a system outage. We enforce things like read-only limits, or if we do allow configuration tools, we mandate a human-in-the-loop workflow. The agent plans to delete an interface, but the system pauses and pings an engineer. The agent proposes this configuration change. Do you approve? Add an authentication, role-based access control, and solid audit logs, and you ensure the agent stays a helpful assistant, not a rogue operator.
And this brings us to the complete, unified architecture that ties everything we've covered today together. We've got the LLM right there in the center as the reasoning brain. It is strictly surrounded by guardrails, the safety rules. It uses RAG as its memory to pull historical data, and it uses tools as its hands to touch the actual network. Brain, rules, memory, hands. Put the whole shebang together, and you have a unified, incredibly powerful AI agent architecture.
What this all points to is a massive paradigm shift. We are moving from a world of human thinking plus computer executing to a world of AI executing tasks end-to-end. In the past, we humans did all the heavy lifting, analyzing data, forming hypotheses, and the computer just ran the script we explicitly told it to run. Now, with AI agents, the system understands the goal, decides the steps, fetches the data, analyzes the results, and takes action. It is a profound shift in how we manage technology.
So as AI agents step out of the chat box and into the real world, what complex workflow will you automate first? I really want to leave you with that provocative thought. As this tech matures, what multi-step, headache-inducing tasks in your daily grind could an agent completely take off your plate tomorrow? Think about it. Thanks so much for joining me on this explainer, and I'll catch you on the next one.